So in this class, what we were doing was vectors. Anybody have any vector homework questions you'd like me to go over, or specific questions? Yeah. Okay, 16. That was one we just were talking about. I think that's the one, tell me if I'm right, where you have a beam like this at 45 degrees. Is it that one? Oh. Well, oh, 16 is that crazy truss, right? Let me just keep guessing randomly.
What question, 14?
16.
Oh, 16 is going to be that one with the weird body.
Yeah.
The 45 degree.
Oh, okay. Yes. Okay, so okay, so you have a cable like that and a hinge connecting it to the ground. And you're given that the string, the rope, has a length of 0.5 and it makes an angle of 45 degrees with the horizontal. And you're given that the coordinates of this point are 0.6, 0.5, 0.6, 0.4. And the coordinates of this point are 0.05, 0.2. And the first question is, I think if the tension in the cable is T, what's the force vector that's applied to that body by the cable? And then part B asks, what's the vector from the hinge to where the cable touches the wall? I'll call it the wall connection. Okay, so for part A, we're going to use two things. The first one is that any vector can be expressed as its magnitude times a unit vector in its direction. The cable tension is the magnitude of the force vector. So we know that this magnitude is just going to be this variable t. That's what it says. Okay. So now we have to come up with the unit vector. And there are two ways to come up with a unit vector. That's all we need now to come up with that force vector. Anybody have any questions about that idea? This is going to be a really important thing. We're going to use this in like every problem we do pretty much. This idea of breaking up a vector into its magnitude times its unit vector. So there's two ways to do this. The first way is if you're in 2D and given the angle the vector makes with some reference, you know, some reference line, then the unit vector is just going to be the cosine of this angle theta, sine of this angle theta. The other way is if you're in 3D and or you know starting and ending points of the vector, you know, end coordinates of the vector. Then you'll do it as like u is equal to b minus a, and then the unit vector is equal to 1 over the magnitude of u times the vector u. So those are the two ways to calculate that unit vector. And you see that all we have left to do is calculate the unit vector. So we know we're going to use one of these two. Well, this problem is in 2D. And we know that that force vector is acting away from the body along that line, along the line of the cable. That's what cables do. And we're given an angle between the direction of that force vector and a horizontal line, right? So we're going to use the first of those two approaches. Okay, so that's the one we want. And so now the way we're going to think about it is, here's our coordinate system. Our force vector is in this direction. And this angle is 45 degrees. So the unit vector is cosine of, you know, it's 45 degrees counterclockwise from the positive x-axis to the vector. So cosine of 45, sine of 45. And that's 0.7071, 0.7071. And now we just multiply that unit vector times the magnitude t, and we get that the force vector applied by the cable is 0.7071 t, 0.7071 t. So what's the point of that? I said we're going to use this all the time. What does that do for us? Why don't we just represent that unknown force as an unknown vector, say fx, fy, and just calculate the two components? See, you were talking. Okay, you were talking. You got your friend in trouble. So what is the point? So we came up with that force vector. We expressed that force vector as 0.7071t, 0.7071t. Why didn't, like, what's the benefit of going through all that trouble when we could just write this as an unknown force vector from the start with like an unknown x component and an unknown y component of fx, fy. What benefit did we get from going through all those steps? You understand the question? We got a direction, so mathematically, I guess, what's the benefit? So yes, you're right that everything we did was right, and we can do it because we knew the direction for the cable. Mathematically, what's the benefit if we're trying to solve for like forces? What's the benefit mathematically of expressing it in terms of the unit vector instead of just two unknown force vectors? Yeah, you guys have an advantage. Yeah, this time you'll remember. Yes, it has to do with the number of unknowns. If you treat this like just a totally unknown force vector, you have to solve for two variables, the x component and the y component. Okay? To solve for two variables, you need two equations. Okay? Once you go through this, if you know the direction, now we have that, even though it's a two-dimensional force, we have that two-dimensional force expressed in terms of a single variable. And so you only need one equation to solve for that. And being able to reduce the number of variables like that is going to be a key to solving almost every problem we do. Because we're always going to be struggling with trying to come up with a way to express things where you have as many equations as you have variables. That's always going to be sort of the main challenge we have in these problems. Okay, so we went through all this, and what we did was cut down the number of variables by one. Okay, and then part B. So now what's the vector? So the vector we want is from the hinge to where the cable connects with the wall. Okay, so we want to figure out the vector that goes from here to the wall. That green is the vector we want. And to solve this, we have to recognize that that vector is equal to the sum of this vector and this vector. Okay, well, so I'll write this as, like if I call this vector A and this vector B, and the green I'll call vector C. Then C, the one we're looking for, is A plus B. Well, A we can figure out because we have coordinates for those 2 points. So A is equal to the coordinates of this point, 0.6, 0.4, minus negative 0.05, 0.2. So that vector A is 0.65, 0.2. And that vector B, we don't know the coordinates at the wall where it connects, but we do know that it makes an angle of 45 degrees with the horizontal. So for B, I'm gonna set up the coordinate system. And we know that the vector we want is this, It has a magnitude of 0.5, and it makes an angle of 45 degrees with the horizontal. So that's counterclockwise 45 degrees from the positive x-axis. And so that vector B is 0.5 times cosine of 45, 0.5 times sine of 45, and that's 0.3535, 0.3535. Yes? Dang it. Okay, so this is positive, and the 0.2 is negative. Negative, positive. Okay, and that makes this 0.55, and it makes this 0.6. And so now the vector that we want, C, is 0.55 plus 0.3535. So that is 0.9035 for X and 0.9535 for Y. Yep. What? I had to switch the signs on that. I think I got them wrong before. Is that coordinate? I think that coordinate's a positive 0.05 and then a negative 0.2. Okay. I just had it written down wrong before. Any other questions about that? What other questions would you like to see? What other problems? What? New stuff? Tired of this old stuff? Is everyone good for now? All right. So the next topic, in a way, the first topic, is particle statics. Well, what is a particle? A particle is an object that you're treating as having 0 length dimensions. So this is what a particle is. And there's an important consequence of it having no length dimensions. Something with no length dimensions, you can't tell the top from the bottom, the side from the side. So things that you treat as particles, you can't deal with its orientation at all. You can't tell whether it's facing this way or that way. So as a consequence, you can't calculate its orientation. when you think of particle physics, you normally think of, like when you hear about particle physics in the news, they're talking about calculations with subatomic particles, subatomic things. And those are so tiny, it makes sense to treat those as having no length dimensions. And so you sort of get in your head that to use particle calculations, you have to be dealing with things that are microscopic. But that doesn't have to be true at all. Really, all you need is to not care about the orientation of the object. And a lot of big objects are treated as particles in calculations. Like when people are doing planetary calculations, most of the time they're doing that as particle physics, because like if you're trying to calculate where Jupiter is at some instant, for the most part, or at least in a lot of calculations, it doesn't matter to you which way the spot on Jupiter is pointing. All you care about is where Jupiter is going to be, because that affects the gravitation that it applies to things and stuff like that. So Jupiter is obviously huge, but if you don't care about which way the spot is looking, you can treat that as a particle. And so when we treat things as a particle, it's not necessarily because they're tiny. It's just because we don't care about calculating orientations. Okay. The governing equation for particle statics is Newton's second law. And since this is statics and we're not dealing with things accelerating, Newton's second law says add up all the forces on the particle. They add up to the zero vector. What about the moment equation? What about the equation? So last time I said there's going to be two different vector equations in this class, Newton's second law, and then the sum of the moments have to be equal to zero. But for particles, we're not going to use the sum of the moments equal to zero, because that deals with orientation. If you apply a moment to something, it causes a rotation, a change in orientation of that body, and we can't deal with that with particles. So notice that because this has to do with particles, there's no rotational Newton's second law. There's no moment equation. Okay, well, so this is it's an equation that has to be satisfied if something's in equilibrium. Since it's a vector equation, you can think of it as multiple separate equations for the different components. So how many independent equations does this give us? So if we're in 2D, then this equation says add up all the x components of the forces, and they have to add up to zero. And then add up all the y components of the forces, they have to be equal to zero. So this gives us two useful equations. If we're in 3D, then the z components also have to add up to zero, and so you get three useful equations. Okay, so let's think about this example that we just did. Okay, say that we're treating this like a particle, and we want to require that all the force vectors add up to zero. Okay. Well, there'd be some, force represented here. I don't want to talk about how we would do that yet. We'll get to that pretty soon. But up here, there would be a force vector applied to the body by this cable. Okay. And this is just sort of getting back to the thing I was saying before about like why would we do that thing with calling this force vector the product of some unknown cable tension and a unit vector. Okay. This is a two-dimensional problem. So how many useful equations do we have from Newton's second law? 2. And so how many variables can we solve for? 2. If there's more than 2 equations, we can't do anything with it. Okay. So this is a case where if we just left that as an unknown force vector, we just said that that's components fx and fy, then we couldn't have any other forces happening in this problem and still solve the problem. Okay. But if we represent this as some unknown magnitude t times a known unit vector, then this vector is represented by just a single variable. And that means since we have 2 useful equations, we can calculate 1 variable here too. Okay? Are you with me on that? Sort of understand that again? So that's why it's always, we have 2 equations or 3 equations, and we're always trying to come up with a way to express all our unknowns with a number of variables that's equal to the number of equations that we have. That's sort of that's the game, you know. But it's not a game, it's deadly serious. Yes. Well, I don't really want to get into it, and it turns out that we couldn't solve this as a particle. We couldn't, we could figure out some things about it, but in order to come up with all the forces acting at that pin, we'd have to treat this as a rigid body and use rotational Newton's second law. Okay, so anytime we use Newton's second law or the moment equation, the moment equation is what I call rotational Newton's second law because it has pretty much the same form. You have to draw a free body diagram. So now, yes? No. That's just this. Okay, so let me go through the steps for drawing a free body diagram. Okay, the first step is to draw a closed outline of the body you're isolating. Closed outline of the body being isolated, or the collection of bodies, you know, or part of a body, whatever you're isolating. And this outline should have no external objects drawn. And no internal details. Okay, so why is that? All that matters in your free body diagram is the boundary between what's included and what's excluded, okay? So we want to draw a closed outline so everything inside the outline is part of what's being isolated, and everything outside of the outline is represented only by the forces it applies. That's what the free and free body diagram means. It means it's free of the outside world, and all of the outside world is just represented by the forces it applies to the chosen body. Okay. So for example, let's say you have a car, and there's a man standing on it. And it's being pulled by a helicopter. And it's sinking in the mud. Okay. And no matter how cool the car is, how much you like the rims and everything, all you draw is the closed outline. It doesn't have to be artistic, but you're trying to clearly demonstrate the boundary between what's in and what's out, okay? That's why it has to be closed, because like, you know, like think back to junior high, okay? And you're like, there's all the cool kids, you know? And you walk over and there's like a gap. They're in a circle, but there's like a gap, okay? And they're sort of looking at you and you're like, am I in or am I out? You don't know, you know? And we don't want that in physics. But if you come up to them, and there's an opening and they look and then they close the opening, then you know, like, I'm out. I gotta find some new friends. Okay, that's what we want. We want to be absolutely clear about what's in, you know, it's the in crowd is all the stuff inside that boundary, and what's only going to be represented by forces. Okay, so that's the first step. The second step is draw all the loads that's applied to the chosen object by the surroundings. For now, when I say loads, I'm only talking about forces. Later, it'll also include couples, but I'll talk about that before we get to it. A couple is, yeah, a couple. So these are either loads with a known direction, or unknown direction. Okay, so then let's just go through those two different categories. So 2A, if you know the direction of the force, or if the load direction is known, draw an arrow in the direction of the force or a double-headed arrow in the direction of the couple for when we get to that. And label this arrow with a scalar variable or value. Okay, so what that is saying is you know the direction, and like that first example we did in class, it's saying that we can come up with a unit vector, and that means we can represent that force vector with only one variable, okay? Like that first example we did before I started talking about particle statics. Okay, a couple is, so it's not relevant for particles, but it will be pretty soon. It is two forces acting in, two equal forces acting in opposite directions at some distance apart. So like if you're watching football and somebody comes in and hits the quarterback up here, and someone comes in and hits the quarterback that way, equal and opposite forces, it spins, rotates quickly face down. Yeah. And so that's what a couple does. You can think of it as a pure rotation. It doesn't cause any acceleration because the force is offset, but it causes a rotation. Yeah. And so we'll talk about that quite a bit pretty soon. Okay, so what if you don't know the direction of the force? So 2b, if the load direction is unknown, then draw an arrow in each axis direction and label it with a vector variable or value. And again, it's the same idea for a couple. In that case, it would be like you have a double-headed thing in the x direction, one in the y direction, and one in the z direction for a couple vector. So I draw it like a little coordinate system. A lot of people draw it with the heads of the vectors pointing towards each other, but it doesn't matter. Whatever feels comfortable to you. Okay. Any questions about that? Okay. So the next thing one more thing before we can do problems. That's contact forces. We're going to deal with contact forces a lot in this class. Normally, we're going to think of contact forces as joints because that's the way it's usually going to arise, like a thing's connected to a hinge here and a pin joint over here or something. but we're going to start out with just three different types of contact forces. This is for particle statics again. So the first one is a cable force. And a cable, well, let me just list them and then I'll go through how you do each one of these. So a cable force. The second one is a frictionless contact between bodies. And the third one is friction contact between bodies. Okay, so the first one is cable forces. And a cable always applies a force parallel to the cable and away from the chosen body. Okay, so let me show an example. So if you have a pulley attached to the ceiling and you have one mass hanging by a cable that goes over one side, call this body 2, and then body 1 is hanging from the same cable on the other side. Then a free body diagram of body 1. There's a weight force acting down. So that's M1 times G. And then the cable force is parallel to the cable where it connects to the body and away from the body, so that means it's this way. And a free body diagram of body 2. There's a weight force there, so I'll call that M2G. And then again, we have a force that's parallel to the cable, so it's either up or down, and it's away from the chosen body, so that way. And since it's the same cable just going over a pulley, that has the same force T. Any questions about that? And again, what it means that you represent that with a scalar variable T instead of a vector variable is that says we can represent that force with only one unknown. Okay. Everything except that magnitude can be calculated from what we're given because it's a known direction. Okay, the second one is frictionless contact. So if two objects push against each other without friction, then the force is perpendicular to the surface of contact. And toward the chosen body. So cable forces are away from the chosen body. Pushing forces are toward the chosen body. So for example, if you have two carts that are in contact and they're rolling along a surface, let's say this one's 5 kilograms and this one's 3 kilograms, and there's 100 Newton force pushing up the ramp. Well, this wouldn't be in equilibrium, but the free body diagram, you still do the same way. So what would those free body diagrams look like? For the 5 kilogram, you'd have a weight force. That's 5 times 9.81, so 49.05 newtons down. And then you'd have two pushing contacts. Where would those be? There's a normal force, yep. And whoops, you want to make it clear in your free body diagram when vectors are not parallel or perpendicular to each other. You should be able to tell from looking at the free body diagram whether they're parallel or whether they're perpendicular or neither. Okay, so I'll call this N5. Mm-hmm. Yeah. Right, but it will matter when we get to rigid bodies. So we're sort of setting up for that in a way. And then where's the other pushing contact? Oh, we're assuming frictionless for now. So the other one is from that other body. So there's a force R there. Yep. Right. And then free body diagram of the other cart. So there's the outline. And there's a weight force of 3 times 9.81, so 29.43 newtons. And then there's a pushing contact from the ground, I'll call that N3. And then there's a pushing contact from the 5 kilogram cart. So that force is perpendicular to the surface of contact toward the chosen body. And do we know the magnitude of that force? Oh, well, there's also 100, but that's not the one I'm talking about. Do we know the magnitude of this contact force? It's equal and opposite, so this is also R. That's Newton's third law. Any questions about that? Okay, and the last one is friction contact. Okay. So this is a pushing contact, but you also have friction. And in physics, when you dealt with friction, you did stuff where you have a coefficient of friction and you calculate the normal force, and then you use the normal force to figure out the friction. We don't have to do that here. And that's because since everything's in equilibrium, we can just calculate what the friction force has to be to keep it in equilibrium. So we're never going to really deal with coefficients of friction. Way later on we will for a couple of select things, but what we're going to do is just represent friction contact as a force vector with an unknown direction, a fully unknown force vector. So a force vector with an unknown direction. Okay, so this is the case where you're going to represent it by 3 components of a vector, and your vector variable, or your variable, is going to be a vector. So let me show an example of this. Okay, so let's say that you have a box on an incline. And the lower box has a mass of 2 kilograms, and the upper box has a mass of 1 kilogram. And let's say there's a horizontal force this way of 5 newtons on the top box, and a force vector parallel to the ground of 10 newtons on the bottom box. And we'll assume that there's friction between the 1 and the 2, and between the 2 and the ground. So free body diagram of the, let's do the 1 kilogram first. There's a weight force of 1 kilogram times 9.81. So 9.81 newtons down. There's the 5 question. Okay. There's a 5 Newton force horizontal. Well, we're only dealing with the 1, so the 10 is not acting on the 1. So that's not in here. But there is, yep, and we're not going to break it up into a normal force and a friction force. We're just going to treat it as an unknown force vector. So I'll just write it like this. Okay. And I'm going to use a notation that calls this the force vector on the 1 by the 2. So this reflects the coordinate system that you use. So I'm assuming that we're just using the regular coordinate system. In physics, you use that rotated coordinate system because it makes it easier to represent it as a normal force and a friction force. But in this class, since we're not doing that anyways, there's no benefit to rotating the coordinate system. So we're just going to use the regular one. Okay, and then the 2 kilogram. So we have the downward weight force of 2 times 9.81, so 19.62. And we have the 10 newtons, yep. Oh no. Ooh, new notification. Okay, so yeah, we also have the 10. And down here, we have the force vector on the 2 by the incline. Okay. Not for particles, it doesn't. For rigid bodies, it will. Because for particles, we're assuming everything happens at the center of mass. Yeah.
And just again, so you're saying that's like just notation, it's not you saying up and to the right.
Correct. Yep. The signs will have to work out on their own. But we're just saying there's an X component and a Y component. And then the last thing is, so there's contact at the top of the 2 kilogram box. So, and that's a friction contact, so it's going to be like this. And I'm going to write that as the force on the 2 by the 1. And what does Newton's third law say about the relationship between the force on 2 by 1 and the force on 1 by 2? Equal and opposite. So this is equal to negative F1, 2. Yeah, that's for sure. You ain't seen nothing yet. Yeah. Okay, so let me write down that notation. So notice this subscript notation, FAB is the force on body A by body B. And when we get to couples, it's going to be the same thing. So it would be a couple, capital M, A, B, and that's saying the couple on body A by body B. All right, so let's do a calculation. Um, so let's say we have a ramp with a pulley at the corner. And there's a 5 kilogram cart over here that's connected to that cable. I can make that look better. And then hanging down from it, sorry, I messed that up. You're gonna have to redraw this. So this needs to be a friction contact. So that box comes all the way down. And let's say that this is a 1 kilogram mass hanging from that cable. And we want to know what's the force vector that's applied to the 5 kilogram cart by the ramp. We need to know the angle that this ramp's at. Let's say it's 20 degrees with the horizontal. Okay, so you could, you look at this and think you want to do a free body diagram and use Newton's second law for the 5 kilogram cart, the 5 kilogram mass. It turns out if you did that first, you'd see that you couldn't calculate it yet. And then that would lead you to isolate the 1 kilogram cart, mass. So I'm just going to do that first. Okay, so first I'm going to draw a free body diagram of the 1 kilogram mass. There's a weight force down of 1 times 9.81, so 9.81 newtons. And then there's a cable force that's parallel to the cable away from the body, T. And like everything in this class, we're going to assume that it's in equilibrium. It's not accelerating. By the way, it could be moving with a constant velocity, and the calculations are exactly the same. All we have to know is that it's not accelerating. And so now based on this, we'll go to Newton's second law. And so we have a downward force of 9.81 as a vector that's 0, negative 9.81. And we have an upward force of t, so that's 0t. And those have to add up to a 0 vector because there's no acceleration. The x equation doesn't give us anything useful, but the y equation says t is equal to 9.81. And so that's why we isolated this first, so we could calculate that cable tension. Okay, so now go to the free body diagram of the 2 kilogram. Is that what it is? 2? 5. So free body diagram of the 5 kilogram. So there's a weight force of 5 times 9.81, so 49.05. And there's a cable force parallel to the cable away from the body. And that force magnitude is T, which we just calculated. So yep, 9.81. Yep, and then we have, since this is a friction contact, we have an unknown force vector. I'll call that force on the 5 by the incline. So these two are easy to represent. The one that's takes a little working is, if here's our coordinate system, the cable force is this way with a magnitude of 9.81 and an angle of 20 degrees. So as a force vector, that's 9.81 times cosine of 20 and 9.81 times sine of 20. Could someone calculate those two components? I think you'll be happy if you do it this way. I mean, I wouldn't mark you off, but yeah, I think you'll be happy if you do it this way. And then in like in deform and dynamics and stuff, we're gonna use that, because really that's a type of matrix, and then we'll do matrix math with it. And this is the notation you'll most likely use in linear algebra too. Mm. Oh yeah, right. Yeah. 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 Anybody calculating that? Okay. So now we can go to Newton's second law. And we have 0, negative 49.05. Plus the force applied by the cable that we just calculated, 9.22, 3.36. Plus this unknown vector, you can write that as components x and y. And it's equal to 0, 0. And now that's just two separate equations, and you're calculating those F components. So F5I as a vector, the X component is negative 9.22. And the Y is positive 45.549. And so that's the force vector that the incline applies to the block. Any questions about that? So I just did it as if it was two totally separate equations. So the first equation says 0 plus 9.22 plus 5 plus f equals 0. That's all for f. And then the second one says negative 49 plus 3.36 plus f equals 0. So I'll put that in. Any other questions? Okay, that's it. See you Thursday.